Hello SFT students, and welcome to the physics video that was promised and now is finally coming up on Saturday. I apologize for the delay, and I make a promise to you to have these ready before you're going to need them, so they will be available, and we will talk in class as soon as we next meet. I'm not sure what day that is right now. It might not even be till Thursday. However, I hope you watch this video, and some pointers are to listen to what I say. I try to keep this as concise as possible, for now at least, and to do this for understanding. If you're hitting pause and sort of fast forwarding through the video just to kind of fill it out, well, first I'll say I'll know if you do that, and I will tell you to please not do that, because it's not helping you learn any better, but also because right now I haven't told you how I'm grading this, so having it filled out is not going to necessarily get you any better score or mark than if it's totally blank. So with that being said, don't fill it out just to fill it out. That's a waste of your time, and in my grading it, it would be a waste of my time. So I don't want to waste anyone's time. I want this to be as quick as possible for getting the information, but yeah, anyway, we'll talk about it. So diving into this, this is the first page. You already have this page and a few other pages. If you do not, there is a link at the bottom of this, in the description of this YouTube video, that will direct you to a place where you can download what we're looking at. The only difference is you might see in here at this bottom left corner, and I'm going to close circle about it, and I'm just trying to figure out, there's a button I can press to forgive me as I relearn my little tablet thing. I want my straight line. I don't want that much of a straight line. I just want to draw a box. And there we go. If I hold shift. Around here you'll see some terms. These are terms that are kind of essential things in the first unit. We're going to call this unit 1. And these are the words that are some terms that you'll need to know the definitions of. Distance, displacement. These two are very similar, and I will talk about both of them. So I'm not going to write down a definition here. In the future, you might ask me to, and then I will do that. Vector versus scalar, x-axis and y-axis, and the origin of a graph. So I will be using those words. These are the words that you will be expected to have a good understanding of. So if after this video you don't understand what any of these terms are, please let me know, and we will find a way to help you figure that out. So what I'm looking at here is a position versus time graph. Typically if you see a position versus time, that means that one of these axes will be describing position and one will be describing time. I will highlight those in colors. So position, where do we see that? Do we see that here on the, we use different color now? Gonna do some annotations. So here is our y-axis going up and down here, y, and in blue we've got our x-axis, which goes left to right, and our position, is that on the x or y-axis? Position is on the y-axis, so I will kind of put a green line here. Position is on the y-axis. And it's a position versus time graph, and we'll see that time is on the x-axis, so that I'll make a little blue color there. If that was painfully boring to hear, well, it's over now. If not, maybe that was helpful. So we'll be looking at a lot of types of graphs, position versus time graphs. The other types of graphs we will see a lot are velocity time graphs, and I'm just going to say VT graphs, and acceleration time graphs. So you'll see position time, velocity time, acceleration time. So that's something you will become familiar with. So on to the actual problem. It says 1, given the following position versus time graph, draw a motion map with 1 dot for each second. Okay, so first of all, I know I'm going to have 7 dots because this describes, I'm actually going to have 8 dots because I know about 8 seconds. So expect to see 8 dots. I'm going to change my marker to something that will make that a bit easier. And I'm going to make my dots, I encourage you to have fun with color. I'm going to make my dots kind of violet. Let me know if you're colorblind or red-green colorblind, and then I will pick colors more appropriate. Also, there's some really cool tech that can fix color blindness, which would be cool to get the class some of that. All right, so starting with the first second, starting at 0 seconds, between 0 and 1 seconds, what happened to this thing? Well, at 0 seconds, the location was at 0, so I'm going to put a dot here. Actually, I'm changing my mind. I'm going to use a pencil. And then what happened during that first second? Well, between seconds 0 and 1, and I'm always reading graphs left to right. So between seconds 0 and 1, the position changed from 0 meters here up to 2 meters. So I'm going to draw an arrow showing that in that first second, 2 meters were crossed. So here I see this motion map, and the motion map, there are a few ways to do it, and I'm actually going to change my arrow, make it a little smaller, and you'll see why in a second. So right now I have 1 second described in 1 second, starting at 0 meters. Now the object, whatever this is talking about, is at 2 meters. And how do I know that? Well, since this is 0 meters and this is 5 meters, I'm going to say that's probably 1 meter. Always include the units, so I'm putting an M there. 3 meters, 4 meters, 5 meters. Okay, and what happened between second 1 and 2? Well, second 1, which is this dot right here, that's the first second, it's at 2 meters, and then 1 second later, it's at 4 meters. So I'm going to draw a line, and right there we're at 4 meters. Now I've drawn all these in a row because it uses the least amount of space. In class we did something different, and either way is fine, as long as it gets the message across. This is clear. If 1 dot equals a second, that the dot started here and went 1 second later was here, 1 second later was here. As long as we agree that each dot is 1 second, then this is a clear way to represent that. Between seconds, the next second, so we have 1 second, 2 seconds, 3 seconds, this dot is just here because it stayed at 4 meters for a whole second. So now I'm going to, since now I'm going to have to show the next second, I am going to go down a line and say that for the next second, it went 1 unit or 1 meter to the left. Ideally, I would put that on the same line, but then we would have 2 lines over each other, and that would be confusing. And then, so second, let me add in a different color. I'm gonna show too much rather than too little here. So second 0, 0 to 1, second 1, second. So I can't really see that. So this is starting at second 0. This is at second 1. It's at 2 meters. At second 2, it's at 4 meters. At second 3, it's also at 4 meters. At second 4, it is at 3 meters. And now we'll continue on with the purple. So what happened at second 4? Well, at second 4, I find second 4 on my x-axis. It's at 3 meters. And then at second 5 seconds here, I look up, that's at 2 meters. So I have an arrow here. And I changed from purple to pink just because I didn't save my color well. And then I know that it goes to 1 meter because the speed or velocity is constant. And then another arrow here. And then it actually stays for a second right here. It's not that it stopped at second 7, it's that it's staying in the same place for second 7 to 8. So I have a dot saying it's at second 8, it's staying there. Now interestingly, do you see that there's an arrow there? An arrow like that, again I'm circling it, I'll circle it in another color too. That arrow means that this goes on forever, so I could actually keep drawing dots, one after the other, after the other, after the other. Here, I'm going to fix this. 1 second, I'm using a tool to carve this color. I could do this, because that arrow means that essentially this object has stayed in the exact same place forever, but we're not going to draw in an infinite number of dots because that's just kind of silly. But you could, and I wouldn't be upset about that, or I wouldn't say that's wrong. It's just that we could. So now I'm going to finish labeling in all these dots. So again, at second 0, it was at 0 meters. At second 1, it was at 2 meters. At second 2, it was at 4 meters. At second 3, it was at 4 meters. At second 4, it was at 3 meters. At second 5, it was at 2 meters. At second 6, it was at 1 meter. And I'm going to check with my graph, and it agrees. At second 7, it was at 0 meters. At second 8, it was at 0 meters. At second 9, doesn't appear on the graph, but because of that arrow, I can make the assumption that at second 9, 10, 11, second 1000, it's still at 0 meters. Now, I am making assumptions there. In physics, we make a lot of assumptions. So the purpose of this activity was just to get you to prove that you can read this graph. If you can make the right motion map, this conveys the exact same information as the graph. So it's just a way to write down to prove that you know what this graph means. I'm going to do something right now that I am curious. I will want your opinion on if you think this is helpful or not. I'm going to open a program called Algodo, which we used the first day of class. And I don't want that, I don't want that, don't want that. And I'm going to create a block. And I'm going to say that it's, I'm going to do some stuff here. Don't worry about exactly what I'm doing. And I'm going to add a plot. So basically, what I'm trying to do here is things are at some point going to get hard, and sometimes it helps to see what's happening and see what that graph described. And I can do that with this program called Algodo, and you can do your own experiments once you learn how to use it. So I'm going to recreate that first problem in Algodo, and please let me know if you think this is useful. I know eventually it will be, but I just want to introduce you to this idea. Again, I'm going to set this because I know that to be true. We have not talked about that, so don't worry if you don't know why I'm doing these things. And I want to show an arrow or a vector indicating which way it's going. Where do I? It's been a little bit since I've used this, so I'm going to show it's going. And what else? I want to see a graph. And what kind of graph did we have before? We had a position time graph. So I'm going to add a position time graph. So that means my x-axis will be time, and my y-axis is going to be position. I've got two options here. Since I decided this block is going to be moving left and right, that's the x direction. So I'm looking at position. So this is the exact same thing. So this is going to create a graph, and I want this graph to last about 8 seconds. And before I start this, okay, so I'm going to play this, and I want to play it for 2 seconds, because that's how long it took for the block to get from, or the object, whatever it was, to stop moving. So here it's going. Can't see it. And I'm running in slow motion just so I can hit pause at the right time. 1 second. 2 seconds, and I paused it almost right. So notice we have a graph here that's going up. And then what happened to the block? The velocity went to, the speed went to 0. And that lasted for 1 second. There we go. And then what happened? Then it moved back to where it started from. But each second it only moved 1, so now we'll watch that. And again, I decided to do this rather spontaneously, but if you think this type of thing would be helpful, I will do it in a more prepared version, and then I will put in some code, so it'll just do what, it'll just show the whole animation, and you'll see kind of what happened. So it's almost back to where it started. And right there, that's second 7. And then what happened to it, it stopped moving. So I'm going to say, hey block, stop moving. And it stays there. So here's the graph. And it's the exact same thing, almost the exact same thing that we saw on the worksheet. Now there's one important difference. I'm going to copy this over, go back to here, and I'm going to look at this. I do want to be a bit smaller. Whoops. Smaller. Great. Whoops. Whoops. All right. There we go. So I hope you agree that these two shapes are the same. Now there's one big difference, and that big difference has to do with one of these things. It has to do with origin. Now in this graph, it started at 0 seconds and at 0 meters. Is that the same thing in this graph? Think about it for a while. It's not the same thing. And why is that? And this helps our understanding of what an origin really means. Recall that 0 meters is an arbitrary decision. And here it says something started at 0 meters. But when I did this simulation, it's saying that it started at negative 2.5 meters. Why is that? Well, that's because I didn't tell it I did not tell the simulation that wherever I just by happenstance decided to put that block is 0 meters. I could have, I think, done that, and then maybe if I had restarted it, it would think, no, apparently it does it by the center of the box. So I would have had to have put the box right there, and then it would have agreed it started at 0 meters. But again, your origin is something you decide to make things as easy as possible. So it would have been, in hindsight, smart of me to have put this where the computer agrees it's 0, or where the simulation agrees it's at 0 meters, but I purposely kind of put it somewhere else to show that, well, it is arbitrary. We get to pick. So these are the same thing. And again, I'm over-explaining things way too much, and I want your feedback on that. If that's really annoying, I want to know. Or if you kind of like that, let me know. And then maybe I can make 2 videos, one where I talk way too much and one where I do it as fast as I possibly can without being incoherent. All right, so let's look at the next page, or the next problem of this document. Come here to sketchbook. All right, so here's the second problem, and this asks us to do the opposite process of the first problem, and I'm going to spend much less time on this one. It says, given the following motion map, let me zoom a little bit. Given the following motion map, again, this thing here that I'm now drawing a circle around, this is our motion map, in case you're not sure what that means. Motion map. And it's just a way of describing motion. So here it says begin. It begins at 5 meters. So now I'm going to translate this motion map onto this position time graph. It's clear here 1 dot is each second, and here I have time in seconds, so I have an idea of what to do with that. And here it says position in meters, and I notice that this kind of number line here is also in meters, so that's great. I don't have to worry about meters or wheels or feet. I'm just sticking to meters. So that makes things easy. So if something starts at 5 meters at 0 seconds, well, I'm gonna make a guess that the beginning is at 0 seconds, but again, that's kind of arbitrary. But I'm going to state that the beginning is 0 seconds. Note that that was never explicitly stated in the problem. Maybe you think that's obvious, but nothing's obvious. So I'm putting a dot there to show that it was there. Okay, then this next dot, so I'm going to cross that out because I've now represented on the graph. This dot represents at second 1. Now at second 1, where is this dot? Well, it's at 4 meters. Because I'll fill this in: 1 meter, 2 meters, 3 meters, 4 meters. So at second 1, I'm going to put a dot right here at 4 meters. At second 2, and cross that out. At second 2, which is right here, is at 3 meters. So second 2, 3 meters. Cross that out. At the next second, which is second 3, it's at 2 meters. At second 4, it's still at 2 meters. At second 5, it's still at 2 meters. But it's moving. But it starts at things, so I'm only putting a dot where it starts at. So second 1, 0, 1, 2, 3, 4, 5. At second 6, it's at 1 meter. At second 7, it's at 0 meters. 0, 1, 2, 3, 4, 5, 6. 7. At second 8, it's at 0 meters. At second 9, still 0 meters. At second 10, well, it's way up at 2 meters. So at second 10, put it out here at 2 meters. And at second 11, which is our last endpoint, it's at 4 meters. Now, this is kind of the best final answer. Interestingly, at the end, it says it's still moving up. So it didn't really end because there's an arrow there. So it says this is the end point, but we know it's still moving. So is that really the end? Not really, because we know it's going to keep going. So, but if it says we're just going to stop here, but know that the particle is still moving, that's fine. If you want to connect these dots, you can, but I urge you not to unless we know more, because is it possible that between seconds 2 and between, say, these two, is it possible that it bounced way up and then came back down? Yeah, it is possible. This motion map doesn't tell us what happened at 2.5 seconds. So I'm going to put like a blue dot. If this happened, it's possible that the particle teleported from 2 meters to 5 meters back to, and then went teleported back to 2 meters. And based on this, we wouldn't know. So therefore, I really don't want to connect the lines, because if I connect a line, it says that I'm assuming what happened to it when I don't really know what happened to it. But again, at this point, if you connect the lines, if that makes you really happy to connect lines, go ahead. And it'll become clear why in the future maybe you shouldn't, because it's making assumptions. All right, going to the next page, and I'm going to be speeding up each time. Don't worry. Back to my sketchbook. All right. Consider the position versus time graph for cyclists A and B. All right. Here I've got let's look at my x-axis and my y-axis. My x-axis here is t. T stands for time. T will always stand for time in physics. Letters are kind of protected in physics. A lowercase t pretty much only means one thing, and that's going to be time, because time is one of the most important things. And that S is fairly, not as protected, but fairly protected. It almost always means seconds. And then here we have X. X here, and this can be a little tricky, it does not mean that this is the x-axis. X is just often used to describe the position of an object. So the position, X is the position, and it's in the unit of meters. Because look, this isn't the x-axis, this is the y-axis. And that can be confusing to see an X on the y-axis, but it's because X means position, and it's, in this case, in the unit of meters. And we've got two, says consider the position versus time graphs below for cyclists A and B. It may help to color code this. So I'm going to use my ruler feature here. I put one dot here, one dot here, and I'm going to trace this, one blue, and then I'm going to trace the other one, red. And I encourage you to do this. There's just a limitation of black and white printing. Okay, so let me just write that out in words, that cyclist A is blue and cyclist B is red. Okay, so what happens? Well, cyclist A starts, and notice it doesn't tell us any numbers here. So this is a conceptual problem. As in, we can't say whether cyclist A starts at 0 meters, or 5 meters, or 10 meters. We don't know. It's not given to us. Only one number is given to us, which is 5. And note that because time is seconds, we can assume that this 5 means 5 seconds. So these questions are gonna take us through take us through being able to describe this, because the goal is to be able to describe what happened here. So I'm going to do that, and then I'm going to put in a little simulation video of kind of what this looks like. So do the cyclists start at the same point? How do you know? If not, which is ahead? Well, our start, as far as we can tell, is right here. So at the start, there is bike A, and there is bike B. And I think it is a very reasonable assumption that the higher up we are on the y-axis, that means more distance. We can also make that assumption because as time goes on, the bikers are getting higher up. So if this is like a race, they're going forwards. So yeah, they're both going in the same direction. So we're calling, this is the positive direction. They're going away from some point. If that didn't make sense, that's okay. That part. But I know that who starts further up? Cyclist B starts further up. So the answer is no, they don't start at the same point. I would like you to answer in full sentences. I may not, just because I need to work on my handwriting on this tablet device. How do I know? Well, I know that, well, here, if I want, I can define this as t equals 0. There's nothing that prevents me from that. So if you want to do that, you could. That's an option. But how do I know? I just know that at the initial state, or at time equals 0, or at the origin. So at time origin, I don't even know if that's a real phrase, but I hope it makes sense. So here's the origin. The time at the origin, so at the time origin, I know that B is at a more positive location, or a higher location. More positive, I think, gets the idea pretty well. More positive location, or not really location, we want to use position because that's what it says. It's a position time graph. And the word higher is also a little confusing because that line is higher, but that can be confusing because this doesn't mean the bikers are going up into the air. They're probably going on like a road or something. But I can see that this dot has a more positive, initial condition, initial state than the blue line, the blue bicycler. And it would probably be nice if I made that dot blue. So at the time origin, B is at a more positive position. So that's a fine answer. At time equals 7 seconds. No, do I see where 7 seconds is here? No, I see where 5 seconds is. But do I know, I'm going to assert that the number 7, that 7 seconds is a larger value than 5 seconds. That's, I think, that does not require explanation. This symbol here, this mouth, that's like the Pac-Man mouth. I'm going to draw a little Pac-Man here. Pac-Man eats the bigger number because he's hungry. He wants the bigger thing. So 7 seconds, a larger value. So on the graph, I could say that 7 seconds is going to be somewhere around here. I could put in a point if you want to. You can. It could, conceptually it's fine, but it could be here, it could be here. 7 seconds could be way over here. We don't know, but I know that it happens after 5 seconds. So I know that if I look at this dotted line, everything to the right of that line is more than 5 seconds. Everything to the left of that line is less than 5 seconds. So 7 seconds has to occur in the area I'm about to shade in. I'll use this like, I've got a little spray paint tool, I'll use that. Airbrush. I'm going to do it yellow. So this area making yellow, I know that that's all after 5 seconds. And if I know that 7 seconds is after 5 seconds, I know we're talking about this orange area. And in this orange area, who's ahead? Who's ahead is the blue cyclist. Because I know that at 5 seconds, A passed, the blue line got ahead of the red line. So anytime after 5 seconds, blue is ahead. So at 7 seconds, that's after 5 seconds, blue is ahead. So blue is ahead. And how do I know? I see that blue passed, and I really shouldn't be saying blue, I should be saying cyclist A, but since I've colored them, this is okay because I've created a definition of the blue rider and the A rider being the same rider. So blue passed red at time equals 5 seconds. So for all time larger than 5 seconds, blue is ahead. And please don't write down exactly what I wrote. Try to do it in your own words so it makes sense to you. Which cyclist is traveling faster at 3 seconds? How do you know? So where's 3 seconds? Well, I just know it's to the left of this line. And how do you know here? Well, we haven't talked about slope yet, but if you're in Algebra 1, you probably heard the word. But since I know, if I know that I'll make this argument. At 3 seconds, I'm going to argue that cyclist A is always traveling faster than cyclist B, or the blue cycler is always faster than the red cycler, because the blue cycler started behind and then passed him, and these lines are straight, so there's no speeding up or slowing down. So I'm going to say the blue cycler is always faster. If he's always faster, that means that 3 seconds is part of always, so at 3 seconds. So thus, the blue cycler is always faster, thus at 3 seconds, the blue cycler is faster. Are the velocities equal at any time? How do you know? Here's a definition. Velocity is a word we haven't defined before, so I should have put that at the start. I will define it right now. So velocity, I will give the formal definition. The change in time, sorry, the change in position there are a bunch of ways I could define it. The change in position divided by the change in time. Also, aka, it's very similar to speed, but it's not quite speed. The other way to say it is also, it is the, so also, or the slope on a position versus time graph. And that's way too big. Where can I fit this? So slope being how steep is this line? Imagine these are like, you know, slides or hills. Which of these hills, I'm going to draw a little dude. I'm going to draw a what color haven't I used? I haven't used green yet. I'm going to draw a little green dude on line A. Here's a little dude. He's trying to climb up the hill. Here's another green dude on line B. He's trying to climb up the hill. Who's climbing a steeper hill? This guy is, because the line's steeper. That means the slope is higher. That means that the slope of this line is higher. That means if we've defined velocity as the slope of a position versus time graph, that means that A, blue, has a higher velocity because the slope is higher, it's steeper. So to answer part D, are there velocities equal at any time? No. A is always faster because that line is always steeper. And I really don't want to use faster. Is always, I'll say faster, fine. Fine, to the wind with convention. A is always faster. The thing that the common mistake here is you might say they're equal at 5 seconds. Now, there's something equal at 5 seconds, but it's not velocity. It's that they're in the same place at 5 seconds. So their position is the same at 5 seconds. So let's see if we're done with that problem, or that question. Oh, we've got a few more parts. So I'm going to do this, and let me just go back and check. Let's see. What do I want to do? I want to paste this here, and that's fine. And then I just want to erase this stuff over here. Ooh, that's an interesting erase. It's erasing the layer. Hold on one second. What I will do instead is I'm going to use a giant eraser that is white. That's not working. Okay, I'm just going to paint it white with a very thick marker. Can I lasso this? Lasso that? Hit delete. Why does it show me that? Okay, I'm going to cut this out because this is just all kinds of silly. Oh, there we go. Big. Okay, I just had to edit some out because getting rid of that in this program was kind of weird. What is happening at the intersection of lines A and B? Intersection means where the lines intersect, so that is the intersection. Right here. And what is happening there? What we can say for certain is that cyclist A and B have the same position. You could add additional information. Always good to say, you know, we don't want to say too much, but if I say this happens at 5 seconds, or this is saying the same thing at t equals 5 seconds, that's great. So draw a motion map for cyclists A and B. So we'll do that. I'm going to use the same colors as I used before. Now here it gives me a 0 meters, and this is now kind of difficult because I don't know where 0 meters is. So I have to decide or say now with conviction that that is 0 meters. I am now going to call that 0 meters at the start. So that the blue cycler starts at 0 meters and the red cyclist starts a little bit ahead of him. Now I see there are ticks here, but I'm not, again, I don't know enough information, so I can't say, if I say that's 1 meter, that could be true, but I don't know that, so I'm really not gonna say that. And do I know that each dot is gonna be 1 second? I don't. All I know is that after 5 seconds, they're gonna be in the same place, so I'm gonna jump ahead, and this may be satisfying, this may be unsatisfying, but I assure you I am doing this with the utmost care. I am placing the 2 dots where I know that they're at the same location. Same location. And how many seconds does that take? 5 seconds. So it means I'm just going to have to put in dots. I'm going to need 6 dots before there. So here I'm going to try to make these kind of evenly spaced because this dot is second 0. I'll put a little 0 there. and he's moving forward, and then he's at position 1, and then he's at position 2, and then he keeps moving, and then he's at position 3, and then at second 4, and then at second 5. And I kind of got lucky, I spaced that nicely, but it's actually kind of hard to do that perfectly. So it's showing that at 5 seconds he arrived at that location. Now I'm going to try to do the same thing with the red dots. The red dots are going to have to be spaced, what do you think, further apart or closer together? Well, I need the same number of dots because the same amount of time passed, so they're going to have to be closer together. So here's at 0 seconds. I'm going to put in the errors later. So I need 0 seconds, 1 second, second 2, second 3, second 4, and second 5. I didn't space those well, so but again, this problem is really hard to do to get these spaced right. And then after that, I can show that I'll put some dots after here, showing that the blue, I'm just going to space them kind of far apart. So this would be second 6, second 7, second 8, second 9. And in red, I'm going to do the same thing. Second 6, second 7, second 8, second 9. So I can pretty see at second 7, who's ahead? Blue's ahead, because if I look at the 2 dots, second 7, the 7th blue dot at second 7 is ahead. It's further to the right. Now here I did some things. I said that each dot equals 1 second. I didn't have to do that. I could have done this much more easily or much more clearly if I said that each dot was 5 seconds. Then I would have only needed like 3 dots for each one. And that's why this is actually a really hard question. Because in the previous page everything had numbers, and now we don't have numbers. And not having numbers can make things harder. We already discussed this. What is happening at the intersection of lines A and B? We already did that. So I think that ends this this page. I'm going to go to Algodo and kind of create this. I'm going to delete this. I'm going to create a cycler A. So I'm going to create this and change its color to a blue. Actually, I'm going to start open a new scene to make this black and white, because that'll be nice. So let's ignore the numbers for now. Any numbers you see, because again, we only know one number, and that's 5 seconds. So I'm going to have this, and I'm going to put text on it. Cyclist A. Is that right? Cyclist A, I said was cyclist A is the one that starts behind. So now I'm going to make this cyclist B, and I'm going to color that red. Whoops, I don't want a red B, I want a red box. Okay. Annoyingly, in Algodo, I believe before I had a red and a blue to help you visualize what's going on. So I'm just going to do that again. Actually, I'm going to add that up. So in Algodo, I want to show you these 2 things. I'm going to have a red box and a blue box. And one of them starts in front of the other. I think the red block starts ahead. The red cycler. I'm using boxes because they're easy to make. I could make a cycler, but I'm not going to right now. And I'm going to give it a velocity. The velocity I give it unimportant, since we haven't talked about how to do this yet. But basically, what I'm about to show you is what's happening, and maybe I'll give some coordinate plane, and maybe I'll start this one here, and maybe I'll start this one here, and just so we can kind of see a background. And when I hit play, we see that, oh, the blue overtook and now, hurrah, has passed red. Again, maybe I'll move this here so time's a little sooner. And we see blue is faster than red. Now I wanted to graph this, but as far as I could tell, it won't let me do that. So I spent the last while creating my own program in Mathematica to show you this, and so I want to show you a graph of kind of what's happening. Again, right here, let me make this a little bigger. So as I slide this, we can kind of see imagine this is a position time graph. You can't see the axes. That's because I didn't want to look at numbers. That as time goes forward, at some point, right there at 5 seconds, blue passes red, and then time goes ever onward. So that's the same thing that's happening as time goes on. Your time is starting, and bam, it's passed, and then from there on, blue has the lead. So yeah, please let me know if you thought like this animation is helpful. Yeah, let's look at the thing. And we're almost done. I've already spent way more time on the first few problems than I anticipated, which I'm not going to say is good or bad, because what I do in the future will again depend on your feedback, because your feedback is very important. Alright, so let's look at these. Okay, and I'm not going to use any simulations or animations until I hear whether those are of extreme importance, and then again I can make videos either that emphasize those heavily or don't emphasize them at all, and then I can have two different options and you can pick which one, the short version or the long version. Again, I'm super open to your input. So 4 says consider the new position versus time graphs below for cyclists A and B. This graph here, which I'm going to put a blue box around, that's what we already just talked about extensively. Now we have a new graph, and then they're different. Well, first I'm going to color in I'm going to shade these to avoid confusion. That's blue, and over here I want A to be blue too. One danger of not coloring them is I could think that like one of them bounced off the other one, and that's just silly. It's supposed to be a very orderly bike race, not one where A bounces off of B. But I am making that assumption. But we have to make assumptions in physics. And cyclist B is going to be red. And I encourage you to use these colors, not only because it helps explain your idea better, but because colors are fun. And I didn't line that up perfectly. Please forgive me that. Okay, so first let's verify that we're looking at the same thing, that these are both position time graphs. This one is position time because I see on my y-axis I've got the position given by the variable x in meters, and on my x-axis I have time in seconds. Here, same thing. So we're comparing apples to apples, oranges to oranges in terms of what the x-axis and the y-axis mean. So how does the motion of cyclist A in this graph compare to the cyclist A in question 3? Well, in this one he started behind B, as in a lower value, That could mean a lot of things, but if I think of this being a race and red got a head start, blue started behind, and they were both going in the same direction and eventually passed. In the new graph, it's quite different. A is going in the opposite direction. Notice as time goes on, B gets further and further and further away from our origin location. And notice that the origin location is this whole line. It's not just that point. It's this whole line where our distance is 0, where our position is 0, away from whatever arbitrary 0 point we set. So B is going, in this case, B is the same. He's going in a positive direction. Here, in this new graph, A is going downhill. Again, if I draw a little, I used green before, I'll use green again. If I draw a green guy here, he could snowboard down this blue line. So it means it's the opposite direction. I said I wasn't going to do this, but I'm going to, just to make sure you understand before you look at the questions, because answering questions before you understand the setup is a combination of impossible and frustrating. So in this case, blue now starts over here, and negative. He's going the other way. So now it's like this. Boom, they pass, maybe they collide. But we're assuming they're not going to collide. If you want more context, how about we have a floor, or maybe we can add some trees or something. Or, I don't know. I'll add a thing that says start. Text, start. Or start. Or B for beginning. Or A for alpha, whatever. And I'll put another post over here to represent. Oops. To represent like our endpoint. Again, they're just to give some context, so it's there. And no, I'm not going to add any trees or anything. That's kind of silly. So we have, again, they're going in different directions now. And the blue cyclist starts closer to the endpoint or further away, and is moving in the direction. Again, if it's useful, I can visualize these velocities. And we can see that they're different directions. And again, we're defining this to the right is always defined as the positive direction. So red starts closer to our definition of the start, or of 0, and is moving in a positive x direction. Blue starts further away from our definition of the start and is moving in the negative direction. Or you can just say, hey, look, the red's moving to the right, the blue is moving to the left. It's the same statement, just different levels of complexity. So now to answer the questions quickly. How does the motion of cyclist A in this graph compare to that of A in question C? So one, if you just say it's different, that's kind of true, but not a very satisfying or complete answer. So cyclist starts further away or just in a different location. Both those are true statements. Further should be further or farther. Further or farther. Don't forget that. I believe farther applies to distance, and I think it's farther. Someone will correct me on that, I'm sure. Cyclist starts farther away, and the other thing different is not just his initial location, he's also moving in the negative direction, or a negative direction. Because the negative direction is okay in this case because there is only two directions. There is the positive direction and there is the negative direction. Those are the only two choices. In other problems, there will be maybe several negative directions. But in this case, I can use using the word "the" is okay. How does the motion of cyclist B in the graph compare to that of B in question 3? They look the same, so they're the same. They are the same. Please use full sentences. Sometimes I don't on here, but it's because I don't like writing with the stylus very much. Which cyclist has the greater speed? How do you know? In the same case, again, speed, that is something we haven't really defined, but blue has a greater speed. Blue. Blue covered more distance in the same time. My argument here is that, okay, in this new graph, whatever time this is doesn't matter. In this time, in red, I'm going to draw, I'm going to draw a line here, and I'm going to draw a line here. So this is how far red moved. Red moved from this location to this location. And in that same amount of time, what did the blue cycler do? The blue cycler, I'm going to draw a line where he started. Again, this line all represents the exact same location, just different times. And this blue arrow we're about to draw, he went from, or she, sorry, I'm so into the patriarchy, moved that far. So who moved further in the same amount of time? Again, it doesn't matter how much time it was, because it's the same for both cyclists, but I can say that this line is longer than this line, so move further. So the speed of cyclist A, or the blue cyclist, is faster. Now you might say, well, doesn't the direction matter? And I would say, well, yeah, but that's going to be defined by the word velocity, which we haven't defined yet. What is happening at the intersections of A and B? Well, here I will give an example of a silly answer. They pass going opposite directions. And maybe they give each other a high five. Exchange high five. And which cyclist has traveled further during the first 5 seconds? How do you know? I already answered that with greater speed. Because I know physics well, I answered this question, I guess, better than intended. So I'm going to say right here, like by the same logic to part C, it's going to be the blue guy. And is there anything left? Draw a motion map for A and B. Sure, we can do that. I want to do that quick. Okay, again, I'm going to start with A. This time, I'm going to make it as simple as possible, in that I'm going to have a starting location. Oops. I have a starting location for blue. I know he's moving that way. And then there's a location somewhere. I'm gonna have a dot for every 5 seconds. So this is at t equals 0. This is at t equals 5 seconds, because I know something special happens at 5 seconds, and he's still moving that way. And this is sometime later, so I'll say this is t equals 10 seconds, just to be consistent that there's 5 seconds between each dot. And as far as I know, he's still moving that way. Our red cyclist, he starts here and is moving, he doesn't start there, he starts more like here. And he's moving. And then I want these dots, it's important that these dots line up. Oops. It's important that these dots line up because at 5 seconds they should be in the same place. And then here. So again, each one is 5 seconds, so this is t equals 0, t equals 5, t equals 10, and it's implied that my units are seconds, but I should always have my s's to mean seconds. Those are not 5s, those are s's for seconds. So that's a perfectly acceptable motion map. And I want to get rid of that m because we don't know anything about meters. To say anything otherwise is to make assumptions, and you know, we could say we're using meters, but then we can't put in any numbers because we don't know. We simply don't know. And just this is pretty quick. One more picture. Okay, going back to my sketchbook program. Okay, an overhead snapshot of Dorothy and Toto. This is an assuming Wizard of Oz walking along the yellow brick road shown below. This makes sense. Dorothy's walking in a straight line. I assume, and let's include this because that kind of thing is important to include. A yellow brick road. So I'm going to use this brush to make a yellow brick road down which Dorothy is moving. And Toto is a puppy, and as we all know, puppies, they like to run around a lot. And it's great. I'm glad Toto is running around here. What is that? Do you think that's is that a tree? Is that the lion? I don't know what that is. It doesn't say. Anyway, unimportant, really. It's not labeled. We can label whatever we want. It looks kind of like a toilet. Or is it like... Anyway, unimportant. We'll say it's a tree. So Dorothy moves in a straight line. Dorothy moves. We could actually measure this. Why don't we do that? Oh wait, that's not exactly... Doesn't do that. Dorothy's line is in one direction, and it's not very long. If you measure it with a ruler, I'm just going to make a guess. Let's say it's like 7 centimeters. I have no idea. Toto, and that 7 meters I'm going to define by the length that this arrow. From that point to that point. That is the displacement, but in this case, so let's talk about distance and displacement. And we'll talk about that for Dorothy. I'm just going to use D, and then in blue we'll talk about Toto. So the distance that Dorothy went, if this line is 7 centimeters long, and again that's just an estimate, the distance she went was 7. Because if you asked her how many steps did you take, she said 7 centimeters. On the map, maybe in real life it was way more than that. And the displacement is the same, because she only went one direction. Now Toto, we'll see this is different. I think we can agree that Toto, because Toto ran this way around here, Toto's experience was running quite a bit further. And it's really hard to measure a curve with a ruler, but I think we can agree that this distance is large. I'm going to make up a number. Oops, I want to use blue, sorry. Say 20 centimeters. Now the displacement is something that we can figure out. Displacement, let's define displacement. So I'm going to type that up in a program that I can do that. I think displacement is the final location minus the initial location. So what that means, I'm going to copy that. Now this is kind of a two-dimensional drawing. We've got both left and right and up and down, so but this kind of still stands as if we don't think of this as just in one direction, but the final position or location, I'm using x, minus the initial location. So basically in displacement, we are completely ignoring the path taken. We are using this definition and not thinking too hard about it. So what I'm going to do is I'm going to draw a line between the initial location and the final location. And that line is the displacement. Again, it's the difference between the final location, where did Toto end up, and the initial location. You notice for Dorothy, it's this it's the same thing as her path because she didn't do anything weird. If I look at her initial position and her final position, I draw the same line that was already there. So one thing that can be said then about displacement is that it is path independent. That means that it doesn't matter what route you take. All that matters is where were you and where are you now. So in Toto's case, what was the displacement of Toto? Well, if Dorothy moved 7 centimeters, then and that was this red line, then Toto's is going to be for sure less than that, and it looks like if this is 7, maybe this is 5. So then we can answer these questions. From start to finish, who travels farther? Justify your answer. There's no right or wrong answer to this. It depends. The word travels is not a really a technical definition. I guess I could look it up because it kind of depends on perspective. So I'm not going to answer this. I mean, if you're trying to think more of who, I guess as I think about it, travels. I mean, often we talk about how far we travel. We traveled from one city to another city, and no one asks, well, did you take any detours? They just ask how far you traveled. So I'm going to say that Dorothy had more displacement, so she traveled farther. She in total she ended up in a place further from where she started. And it really depends. Again, travel is not a technical word. It's not a word used in physics because it's vague. Okay, it developed 2 different definitions for measuring how far something travels. I've already done that. I've said one is like, definition 1 is like your pedometer definition, or your, if you have a GPS watch or something, it tells you how far did you personally move. And this is kind of, if you're more interested in that person's experience, that would be distance. Definition 2 is path independent. It's a little less caring, maybe. Displacement, which has a mathematical definition. All right, I'm sure that was way longer than you thought this was going to be, given this was only 3 pages. So I do want your feedback, and A lot of this you may have already known how to do all of it, but I can guarantee that when this gets to stuff that's hard, and if this was hard, that's fine. A lot of people find this hard, and typically almost no one gets two definitions for number 5 if I haven't explained it beforehand in my experience teaching. So I think you will appreciate this being long when it's confusing, and you will be more confused later on because things get very technical. So again, I hope you will have watched all of this, and I want your feedback next time we meet. All right, thanks, and have a great weekend, and I will see you next time I see you.